Welcome everyone. It's wonderful to be here with you and to have the count continuing. As you might know, it was considered to be last night a 40% chance of the launch proceeding, but it does look as though we're live. So very happy that we have a number of questions here. What I think I might do is take a few of them and we'll try and distribute them around the panel. And then at approximately 5:35 or 5:36, we'll cross to the main live feed for the launch itself. So let's start with the first of the questions. What is the most exciting scientific gain that we'll get from CUAVA 1? I'll answer this one since I might have a better bird's eye view. So we have a lot of scientific gains that we're hoping for, but quite a few of our instruments are also pathfinders. So the next generation will be even better or significantly better. So if we start with ISTI, the imaging instrument, we're expecting very good pictures and spectra of the Earth. For instance, looking at blue carbon sites, marine coastal environments. The Tiny Toll instrument, I will let Chris answer a more detailed question later on, but I'll basically say that they're intending to use the diffraction patterns for binary stars to be able to put that into interferometric mode and be able to see exoplanets in the next generation of this instrument. For the GPS, you will have heard from June that we're looking at much faster acquisition of the GPS signals and decision and evaluation of what our position, navigation, and timing is. So determining orbits. For the solar cells, we actually have technology demonstrators for solar cells. And then the EDIS's instrument Rush and the radiation counter are coupled nicely because the radiation counter will detect energetic particles hitting the spacecraft and causing the single event upsets that hopefully EDIS will be able to detect and then evaluate how well the various modules are able to scrub those upsets from the system and get our system working again. So that might be a quick question. That would be my answer there. Is there anything that any of the instrument leads wants to add to that? Not at the moment. Okay, so I think we have a question here that I wanted to pass to, or have maybe Ijun Wang or Shuliang comment on regarding the data over power network and this question about integrated wires. You know, in other words, why is the data over power network a significant improvement potentially compared with having a lot of wires on the spacecraft? Any comments there, Shuliang or Ijun, if you're here? No. So Shuliang?
So the data over power is to significantly reduce the number of wires on the on small spacecraft. This may sound trivial, but actually the cables or the harness on the spacecraft cause a lot of issues during the integration and during the launch period. So the objective is to modulate the data signals on the single power cable to pass the information through together with the power. So this way we save a lot of space and reduce a huge number of cables for the spacecraft.
Okay, I've just been told that apparently the launch is partly delayed. We're trying to find out whether it's in one of the standard delays, such as the 2-minute delay. We wouldn't be there yet. It could be in the 5-minute delay.
Eber.
Yes.
The SpaceX Twitter feed is saying, standing down from today's launch due to weather. Next launch opportunity is Sunday, August 29th at 3:14 a.m., which would be around the same time for us. Again, tomorrow.
Okay. Okay. Well, that is very disappointing. We're all here. We've got our party clothes on. Some of us at least have our suitable drinks. I have a CUAVA cocktail in this. with guava juice for CUAVA, of course, rum, pineapple juice. And I hope that others will be having something. But let's continue on for the moment. We have an opportunity to answer questions for people. So let's try and do that. So here's a question from Keith about how much of the CUAVA 1 satellite bus is based on Inspire and UNSW ECO, and do we have a standard CubeSat bus as such now? So maybe June and Shirley Ann, you might be the best ones to answer this.
Shirley, you want to go?
Maybe, yeah, June, you.
Yep. So
maybe you want to.
For the Inspire 2 and UNSW ECO, we've actually used a fully GOM space system bus, and some of a combination of UNSW and University of Sydney instruments. Whereas in this case, we've swapped into using a mix of multiple manufacturers of the system bus, and also we've used a QBOS operating system, which is operating system on the onboard computer that is agnostic to the manufacturers of the OBC. So we're going to be able to see our software being ported over to any OBC that is compatible in the future. So we're not manufacturer locked. So that's the benefit of transitioning over in this case. And I'm sure Shailan can explain a lot of benefits of why we're doing this way. So go ahead, Shailan, if you want to add on to that.
Yeah, so one of the major change, like Drew mentioned, is we are changing from a GOM-based exclusive software into a open source platform called QBOS. The main benefit, obviously, is the using the open source software, we can evolve through different missions, and the software is agnostic to the hardware, so we can change different microcontrollers and different computers that are compatible with the platform. So it's essentially a Linux. So in principle, you can probably put a Raspberry Pi or a BeagleBone Black, those cheap electronics to run the system, to run the operation system. So this provides us a lot of flexibility in for the future missions, and a lot of flexibility to build in-house design hardware instead of buying the commercial off-the-shelf one. So as a group, we also intend to open source the QBOS software we developed for CUAVA 1 satellite. We will be, after the CUAVA 1 satellite is validated in space, will be sort of open source everything we have, just to contribute to the community. Yeah.
Okay, excellent. Okay, so we have some questions here, one from Graziella Caparelli about what will happen once CUAVA's on the ISS. And Jason Held has answered some of that already. There's I guess a follow-up question is whether from Peter Aylward, is the CubeSat powered off when it's inside the space station, for instance, and how does it become powered? Who would like to answer that one? Maybe Shirley Ann, would you like to go for that?
Yeah, so the satellite has 3 sets of kill switches, so to speak. So the kill switch is, they are kind of integrated on the satellite and stood inside the deployer. So all 3 of the kill switches, 3 sets of kill switches are pressed down so that the battery is disconnected. Once it's deployed, after it's injected out of the deployer, all 3 kill switches will be on or connected in a sequential order after it's inserted into the orbit, and the satellite will be turned on right after that. We do have a radio inhibit for a number of reasons. We won't be transmitting anything. We won't be deploying our antenna for the first half an hour period. Then the satellite should be sufficiently far away from the space station. Then the antenna will be deployed, and the housekeeping beacon will be sent down to the Earth. Forward back to you, Emer.
Okay, great. So there's a question whether this recording will be available later, and the answer is yes, including the Q&A. See whether we have any other questions at the moment. think the answer is that we don't have any others at the moment. Maybe I'll just expand a little bit on Shirley Ann's answer about the satellite. So as he said, it'll, once the satellite is deployed, it comes free of the tube that it's kept in. And it's released by a door opening at one end and then a spring at the other, basically going ping, just like in Monty Python, and pushing the satellite out. And it'll go out at about a couple of meters per second, which, you know, is relatively fast here on Earth, but compared with the space station, which moves at about 7 kilometers a second, it's very slow. So it will slowly separate from the space station, and after 30 minutes, as Shirley Ann, it will start to come alive, and it will fly freely. So there's no wire or string or anything attaching us to the space station. We instead will drift apart from it, and our orbits will diverge. And over time, the satellite will be hitting air molecules, and some of the satellite's kinetic energy will go to heat up the air molecules and to speed them up. And the satellite will lose energy and slowly spiral into the Earth. Eventually, the collisions will become, with air molecules, will become frequent enough that will start to heat up significantly and eventually will burn up. And that should be of order a year, 18 months until we do that. And that partly depends on whether our satellite will spin or tumble, which is not how we want it to fly. We want it to fly in a nice stable orientation. I'm not sure that I can show this, but a nice stable orientation as it moves around the Earth. And that's so that we can point the camera, for instance, at the Earth and at other sources, the ones that Chris is interested in, and we can receive the GPS signals nicely for June, for instance. Okay, so there's a question here. Okay, so let me just look at the, we're meant to be trying to put most of the questions into the Q&A rather than into the chat. Okay, so I will keep doing that. So question here, what do the 4 stars in the mission patch represent? And really that's an artist's impression. We did want it to be some of the stars of the Southern Cross, but you can see that they're not quite in the right orientation for that. So we tried, but what we wanted to really show was CUAVA 1, so to speak, coming in as part of the new dawn, so to speak, for Australian space science and engineering. So a question from Andrew Barton. Maybe Shirley Ann will know the answer. What data link protocol does the data over power system use?
Okay, the downlink is GMSK for the downlink. The uplink is also GMSK, if I'm not mistaken, for 9K6 BPS. Yeah.
I suspect that Andrew's not referring to the telemetry back and forth between the satellite and the ground stations, but instead the encoding of information in the data over power network in
the data.
regions.
Right. Okay. So that one is not using any data protocol. We're simply sending the data, the raw data from one microcontroller to another. I think the intention is to, in the near future, we'll be integrating that into a CAN bus, which probably will be more common on CubeSat. But at the moment, for this particular mission, we're only sending the raw data. So.
Okay. We have another question from Jules in this case. When can we expect telemetry and what are the final frequencies and modulations? So let me answer that. We're going, well, tomorrow now, we are going to the International Space Station on the rocket, and it'll take, they will then unload the Dragon the Dragon cargo capsule there, and our satellite will be put in the deployer on the outside of, I think, the Japanese Kibo module, and it will be there for about 5 weeks. and we're expecting to be deployed into space in approximately the first week of October. We'd, of course, like it to be earlier, but we understand it to be that first week of October. And so within 30 minutes of deployment, we're expecting the spacecraft to at least try to power up. If it has enough energy in its cells still, then it will be able to turn on. If, on the other hand, there's not quite enough energy, then it will need to be in the sunlight for a while, charging up until it gets to a certain level at which it can run the computer properly, and then an even higher level at which it can deploy the antennas and establish communications. So we're looking realistically probably at about a day or so after deployment that we would hope to have communications with the spacecraft. And that'll be really exciting because we will be the first Australian satellite to communicate with the Responsive Space Operations Centre or Mission Control Centre down in Adelaide, which is built for the Australian Space Agency by our partner Sabre. So that will be very exciting. Details of the frequencies and the modulations, surely Anne might remember them off the top of his head, but they're in the amateur band, the 70 centimeters and 2 meters band for the uplink and downlink, with the higher frequency one corresponding to the downlink. And we'll be putting detailed information about this out to the, for instance, the International Amateur Radio Union people, the SatNOGS people, and other people who are interested on our webpage. But we're not quite ready to put that information out. But it will be coming because we really do want to work with the so-called amateurs, who of course are extremely professional in detecting and decoding signals. What other questions might we have, or any things that members of the panel would like to comment on? For instance, any improvements on discussion about Tiny Toll for the Breakthrough Initiative? Chris, anything else you'd like to say there? Oh, you're still muted, I think.
Oh, it should be back now.
Yep, it's good.
Yep. So the main thing there is basically that it's kind of a precursor tester mission that we managed to include on the CUAVA one, which has been quite nice. It's not capable of doing the actual science of doing the precision astrometry of the star system to actually see those planets, but it will let us kind of test the technology a bit and prove it in space, which makes it a little bit more reliable when we scale it up to a much bigger instrument to actually do that science. And I guess it would add the extra little bit to it is the reason we want to do it in this way is the current techniques that get used. So there's radio velocity, where you're measuring the wiggle of the star and the changes in color of light caused by that, which is very, very small from a Doppler shift, and transits, where a planet goes in front of the star. So far, haven't been able to determine if there's a planet around a star system like Alpha Centauri, mainly because there's stellar effects that happen that, depending on who you talk to, might call them noise, or some astronomers would say there are a lot of interesting information about the star there, but it makes it very hard to determine if there's a planet there. And so we're going for this more direct measurement, but it's still very small measurement. So we're basically, we'll be measuring an offset which is of the order of the size of an atom on the detector. But the funky diffraction pattern that gets put on the telescope pupil lets us do that with some engineering help.
We actually have a few more questions, and there's one for you, June. Is this the first time Australia is doing reflectometry from space?
To my understanding, GNSS reflectometry, we would be the first attempt, although the actual first attempt was UNSW ECO, but we had actual technical difficulties with that one. So this is our second go with CUAVA 2, and we are a bit more conservative this time, giving CUAVA 1 a go at just our GPS operations. And then moving on to CUAVA 2, which has actual support for the reflectometry. So we're more conservative this time as opposed to our ambitious goal back in UNSW Eco.
Okay, excellent. So I have a question from William Lind. What method of attitude control does CUAVA use? So Shulian, perhaps you'd like to comment on that.
Yeah, so our satellite have a single reaction wheel, and we can detumble the satellite using the magnetometer on board, but we can only rotate the satellite around a single axis. But because for the instrument on board of the CUAVA 1 satellite, we don't really aim for high pointing accuracy. So as long as we can rotate the satellite to nadir pointing and zenith pointing, that will be good enough. For the next satellite, we'll be having 3 reaction wheel, higher pointing accuracy, and that will be equated with a star tracker to improve the pointing accuracy as well. But for this one, we only have a single reaction wheel.
Okay, great. So this question here about the biggest challenge our team faced on CUAVA 1 besides COVID. COVID was certainly has been an issue for us. Any comments from our panel here on what they found the biggest challenge? If you don't have anything, that's fine. You can say nothing or not as you wish.
I'll pipe in with them. The software is always tricky. Like we've got multiple payloads that we're all trying to get talking to the main computer, and we're testing on engineering models, and then it goes to the flight model, and things are slightly different. So that's always, it was some fun times in the lab, I'll say.
Yep.
Yeah, okay. I think there were definitely a few scary moments, definitely. But I think in all CubeSat projects, it's a very common occurrence. But I think it's worked out well for us. So.
To me, I think managing a large student team wasn't easy, especially many of them involved for a relatively short period of time. It's difficult to sort of handle things. But I think we did that quite well, and all the students involved are quite responsible, and we actually never had anyone drop the ball. So yeah, I think it's quite a nice job we did as a team, I would say, to integrate this one together.
Edis, do you have anything you want to say, perhaps relating to the quickness which you had to respond?
Yes. Look, I think the software was the main thing, trying to interface the payload with the onboard computer and setting up the test rig for it, right? So, but in the end, it worked out. It's great. So we're looking forward for the launch tomorrow, and keeping the fingers crossed when we are deployed from the space station to get some results. So, but yeah, that was stressful days and weeks, but we got there.
Mm-hmm. Right, so we've got one, I'll come back to Jason in a moment. So I might just answer these ones myself directly, very quickly. So Curtin, yes, we do know that our colleagues at Curtin, led by Phil Bland, has a satellite called Binar 1, which is riding up with us and will be deployed from the same deployer as us. Both of us are using a Japanese company called SpaceBD. And so we've cooperated with them in terms of passing the fit check case back and forth between us in a collaborative way. We've otherwise mostly worked independently, not for any particular reason. And we're looking forward, however, to collaborating with them in the future. For instance, on our Waratah Seed CubeSat project, which is with New South Wales Government, where we will take payloads from others and fly them for money. There are potentials there for collaboration and potentials for some of our payloads to go on their future Binar satellites, and for some of theirs to go on one or more of ours as well. So we're looking forward to that. And we would be happy, think if the frequencies are commensurate, to detect their radio signals and help them with telemetry. Question about the design life of CUAVA 1, I'll answer that quickly and say that we're looking at, approximately 18 months in orbit, but between 1 and 2 years is the likely one. And we anticipate our spacecraft will be able to, is built perfectly well for that sort of lifetime, probably slightly longer, but we won't get that longer lifetime because of atmospheric drag. Let me come rather unkindly perhaps to Jason and say, is there anything that you would like to say, Jason? You might not have been able to look at the Q&A.
No, I saw it. I saw it. Look. I think you answered all the questions that you needed to. Just wanted to say congratulations. Really happy for you. Really excited. I know how hard all of you worked. Julien especially. Mate, you're an absolute legend. Great engineering team. It's been a lot of fun working with you. Just looking forward to getting your baby in the sky. Really, that's what it's all about, man. I brought some of my own special alcohol to celebrate with you. We could always do it tomorrow. All these things, pretty normal stuff, flight delays are normal. It's part of the job. It's part of the industry. One day delay is not going to kill us.
No.
And it's special challenge. Usually what we're going to be looking for is that satellite is going to be deployed in a month and a half. It's going to be in space in cold storage for a while. So there's a process of letting it warm up a bit. Even though it turns on, sometimes the batteries are drained. So you got to let the batteries fill up. And it usually takes up to 2 weeks of trying to contact that satellite before you could actually find it. That's definitely something that we've got a lot of experience in. So we'll certainly be looking for it and deconflicting with other pieces of debris and other satellites in the sky. But at the end of the day, we're here for you all, and we just want to see you have a good flight. So good luck.
Well, thank you. You're part of the team, of course, as well. So we're looking forward to that very much. For tomorrow, we do have a question for you to think about, and that is, what is your favorite space movie, in particular sci-fi movie? We'll leave that question for tomorrow, because what we need to do now is to sign off and thank everybody first for coming to this first attempt for us to launch CUAVA 1, and I think we've enjoyed it. We look forward to coming back tomorrow for sure, for the second attempt at the launch, approximately 20 minutes earlier than this. We will have to get back to you as to whether we will be able to run a launch event like this again, because there's a certain amount of booking that has to be done for the webinar and so on. But we will be in contact with everybody. If you don't get an email from us, please look at the CUAVA website and follow the directions there. But thank you very much, and we look forward to going into space tomorrow.